Thank you for joining us. We are really happy to have you here. And this is our Unit 8 Talks, our webinar on series on data and AI. And for those of you who are new to any Unit 8 Talks and the series, we are Unit 8, a Swiss data analytics and AI company, driving the adoption of data science in the industry and willing to share our best practice. This session is for you, so you have a Q&A section where you can ask questions, and we'll be really happy to answer your doubt and any curiosity. So this session will be recorded. You will receive the video later on, and we're going to publish the final video on our YouTube channel. And without any further delay, today's topic is about learning how to make use of your unlabeled data. And we have Mos, our end-to-end data scientist, Vincent, data scientist, and Yassir, machine learning engineer specialized in neural network. Thank you, everyone, and Mos, the floor is yours.
Yeah, thanks a lot, Billy. So hello, everyone. It's very nice to talk to you today, and thank you very much for joining us on this webinar. I hope you can see my screen well, and I will start. Yeah, so like this is kind of the big message. What happens when you don't have enough labeled data? Well, as a data scientist, kind of, I don't know, your life is over. No, not really. But yeah, that's where the problem sometimes starts, that we don't have enough data to do machine learning, and either we do kind of low accuracy machine learning, or we end up having some kind of rule-based system. So you have rules here and rules there, and for every small thing you make a new rule. And the problem with that is that's not like very maintainable and sustainable. So what can we do? Let's first very like officially state what's the problem, what do we want to achieve. At the end of the day, we want to train good classifier models which can categorize your data. So which means that given a model or the brain of your system, if you see the pictures of cats or dogs, for example, you can say this is the cat and this is the dog, and that's your label. And so like to train good classifiers, you traditionally need this labeled data, and usually quite a lot of them. So for example, you want to train a classifier to discriminate between cats and dog pictures. You provide a lot of cat pictures, you provide a lot of dog pictures, and you say which one is a cat and which one is a dog. So that would be your labeled data. But the problem is the typical company setup is that most companies, for the problems they have, which is not usually the cat versus dog problem, they don't have thousands of labeled data, but they might have a lot of unlabeled data sourced from within the company or from public sources, and maybe a few labeled data that they manually label, for example. And this is the setup we target. So models should work in this setup to address really real-world problems. So yeah, you have a lot of data points. Most of them are unlabeled, and a few of them are labeled. Yeah, so that's the flesh of the discussion. Today we will go over different methods of learning with unlabeled data. So we start with semi-supervised learning. We will talk about pseudo-labeling, unsupervised pre-training, and consistency regularization. Then there are also approaches on zero or few-shot learning. We will not discuss them today for the sake of time, and also for the fact that they're a bit different, like philosophically, and they are more towards meta-learning. So it's not the scope of today. And also at the end, we will also mention one graph-based approach, which is quite interesting. And we finish up with actual real example. So Vincent, the floor is yours.
Thank you very much, Mos. Okay, so let's get started with the grand topic of semi-supervised learning. Let's just jump into one of the definitions. So semi-supervised learning includes using unlabeled data in conjunction with labeled data to improve the performance compared to the case where we would have just used the labeled data. And as you can already see, this pretty much tackles our goal or our request of using also the unlabeled data, like that we want to learn with just few labels. Yeah, so before we jump into specific methods, let's just first try to understand how does semi-supervised learning even make sense. And for this, we have some nice schematics. Yes, so here we see on this left image, the case where we have 4 data points with labels. We have 2 positive ones, 2 negative ones. And if we would now take these 4 data points and train a classification model on top of them, we could get some decision boundary like the one drawn with the red dashed line. And if you just look at those, it sort of makes sense. But then if you take into the picture all the data points, even the unlabeled ones, so you sort of take a step back and look at what is the ground picture, then all of a sudden this red decision boundary seems not so nice. And in fact, you might want to adjust that decision boundary to be more towards the green one in this last picture, because it seems to better separate the 2 clusters. And now it needs to be said that even though this seems quite intuitive, this is not just trivially true, right? The fact that the green one is desired over the red one is a following some assumptions. And these are 3 assumptions that are usually made in semi-supervised learning. Not all of them necessarily, but at least one of them should be made in order for the theory to make sense. So the first one is called the continuity assumption. And it basically says that points that are close together also are more likely to share a label, which sort of makes sense. If you think about an image of a cat, if you change it slightly, if you rotate it, or if you change some pixels, you are not suddenly getting a dog, right? Most likely it will still stay a cat. So this is basically the continuity assumption. Then we have other assumptions like cluster assumption. And there it says basically that your data forms clusters, discrete clusters, and points within the same clusters are more likely to share a label. I think this is also pretty intuitive. And then the last one is called manifold assumption. This is not directly linked to labels, but it says that your data or the data probably lies approximately on a lower dimensional subspace or lower dimensional manifold, and that you can use all the data, even if they don't have labels, in order to learn that manifold. Conceptually, you can think about the space of all possible images of a given dimension. It's huge, right? It includes all sorts of noisy nonsense images. But for example, in order to explain just images of animals, you don't need the whole dimensionality to express those. Probably you will use fewer dimensions to explain these images, and therefore they sort of lie on a lower dimensional manifold. But we will see a better example later on. So going to the first method, which is pseudo-labeling. And here, this is pretty basic idea. It originated in 2013. And the idea pretty much is use your labeled data set to train a model. Then using that model, predict the label for all the unlabeled data points. And then now you have a lot of labeled data points, retrain the model, and maybe do this several iterations. And yeah, the idea is pretty straightforward. And unfortunate, or not unfortunately, but yeah, it's not working that well. That's one of the cons. And in fact, over the last several years in the semi-supervised learning research, that method particularly hasn't seen a lot of attention. The later methods that we will present are favored over these because it doesn't give us state of the art. However, one pro of that method, or one advantage, is that it's domain agnostic. So it works for any sorts of data. Even like other methods, they usually rely on data augmentation techniques and therefore are more tied to the to the data domain. And this, we don't have it, so we can use it wherever. Yeah, another con is that the iteration, due to the fact that we have to iterate, it takes a bit more time. And yeah, not going too much into details here, even though we didn't see a lot of research, we did see 2 ideas that can be summarized in, let's just not use the wrong pseudo labels, because that's the primary reason for why the method doesn't work that well. So one basic idea is just use also the model's confidence score. If the model says, hey, this is a dog with probability of 51%, then we are not using that pseudo label because we think it might be wrong. And then one follow-up idea is that they observe that even if the confidence of a model is high, the output might still be wrong because it might be wrongly high confident. So therefore, we add another estimation of how certain can we be that the confidence score of the model is right. And then we take only those pseudo labels that have a high score and we are certain that they are right. But it still doesn't quite give us state of the art. So we go to the next method, which is unsupervised or self-supervised pre-training. And here, the idea basically is that you use your unlabeled data set in a first step to pre-train parts of your model. And then in the second step, you use your labels on top of that pre-trained part to basically fine-tune or adjust the model to give you the good performance. And here if we go a bit closer into the first step on the left side, we see that the network, it's going from bottom to top, has 3 parts. The first one is green. You can think of this as sort of an encoder that takes your data point and maps it to a nice vector representation, which is in yellow. And then we have the blue part that basically takes the vector representation and produces an output depending on what's unsupervised pre-training you're using. So in this first stage, we really only care about tuning or training the green and the yellow part. The blue part we are going to throw away because we just need it for this auto-regressive pre-training. How specific this pre-training looks like will be more clear in the next 2 slides, but for now, just bear with me. Then in the second...
Sorry to interrupt. I just have one question about this slide on the chat. So I'm just going to read it. In the fine-tuning stage, do we keep the weight of the encoder frozen or do we train them as well?
Oh, okay, that's a good point. Yeah. So in fact, you can do both. If you take over the green, the encoder and the representation to the next stage, normally I see that, or normally I would just also train them. I wouldn't keep the weights frozen because it allows for more flexibility, but you can also just freeze them and use a fixed representation. I think the trade-off here is that if you allow for fine-tuning, or if you allow the gradients to flow all the way through, it will take a bit more time to converge and you might maybe overfit, but yeah, but it gives you more flexibility.
Thank you, Vincent, for the answer.
Thank you for the question. So yeah, going on to one particular example, which is this unsupervised pre-training using autoencoders. And here our pre-training phase basically has an autoencoder. It has an encoder and a decoder. The blue thing here is now the decoder. And we basically train on the mean squared error between the input and the output. So we ask the network, please give us exactly what we are giving you. So input is equal to output. And at first glance, this might seem trivial. However, the clue is that in the middle, we have one layer, this yellow low dimensional representation. It has low dimensionality and therefore acts as an information bottleneck. And therefore, we sort of force the network to learn a meaningful representation of the data. And then in the second step, we use that representation, and on top of which we then do our supervised fine-tuning or supervised learning with the labeled data points. Yeah, and now another example. So just briefly, there are a lot of different examples of this framework. We just picked 2, but yeah, I think there are many more. But one famous one is the BERT style or big language model pre-training that you see here. So in the first step here, we basically, because it's text, we have basically millions or really billions of samples on the internet for free. So that's what we take, and then we pre-train our BERT model on masked language modeling or on next sentence prediction. So basically we give in a sentence, we mask some words, and then we ask the model to predict what were the words that we masked, basically. We train it, and then we produce one pre-trained BERT model, which then in the second step we can reuse. We can maybe add another layer to transform to get our desired output, and then we fine tune. That's the whole idea. And yeah, I think with that those were the first two methods, and I hand the mic to Yassir, who will talk about consistency regulation.
Thanks, Vincent. Yeah, so yeah, you can jump to the next slide. Yeah, so basically consistency regularization, it's a technique that's used a lot recently in semi-supervised learning. So the main idea is that even though we don't know the label of the unlabeled data, at least the model should be consistent. So if we have some image, let's say it's a cat, even if we change a few pixels, even if we add some noise to the model, it should still be a cat, basically. So that's the main idea on a high level, and then there's different approaches. In terms of training, it's usually done in parallel with the typical training. So you have your labeled data, you train your supervised lots as usual, and then you also have one batch at a time, the consistency regularization. So you usually add some noise, as we said, either to the image or to the model, and then you have some kind of consistency loss on a very high level. That's what it usually looks like. Then, so we go through a few examples. So one example is of an approach is to apply basically augmentation. So there's a lot of different image augmentations we can do. So we have, for example, an original image of a kiwi bird, and then we apply some image augmentations, and then we know, even though we don't know the label, we know it's still the same label as the original image. So we pass these two through our network, and then we get two predictions. We get the original prediction and the augmented prediction. And then we say, okay, we don't know the label, but at least they should be close. So we apply a loss there. And then you can look at it in terms of the cluster assumption. So when we assume we have two clusters, if, for example, in here, the red dots, we have two red dots, so one is an augmented version of the other one, then the decision boundary shouldn't pass through it. It should pass outside of the cluster. So we're moving the decision boundary outwards. Another approach is to say, okay, the model, we don't know, again, obviously the label of the image, but the model should be consistent with its previous predictions. So we can add some augmentations to the image. We can add some noise to the model through dropout. And then it should be, we have a consistency loss with the moving average of the predictions across training. The disadvantage here is that we need to store these moving average predictions during training. So there's another approach, which is the next slide. And so here they don't store the moving average of the predictions, but they store the moving average of the weights of the model. So you have another model, which is called the mean teacher. And yeah, it's basically, it's updated not through SGD, but rather through the exponential moving average of the weights of the student model. And yeah, basically you get two predictions. So for each image, you get a prediction from the student and from the teacher, and then the student shouldn't be too far from the teacher at any given point. Yet another approach, which is a mix of different ideas. So the idea here is that you have two images from your training, from your unlabeled training set. Again, we don't know the labels, but we can interpolate directly between the images, and then we get an interpolated image. And then the assumption is that the prediction of this interpolated image should be the interpolation of the predictions of the other two images. And then we use so we have a student model where we get a prediction on the bottom of the interpolated image. And then we want to create a target, so a label that we don't know for this image. And so we pass the other two images, the original images, through the mean teacher. and then we take the average of these, and then this is our target label. And then you can see it also in terms of the cluster assumption. So you have, let's say, 2 points that belong to 2 different clusters, so a red dot and a blue dot, and then it will move the decision boundary somewhere between the 2 dots, which is likely to lie outside, kind of between the 2 clusters. So they won't both be on the same side. Yeah, here's just a bit of code for those who want to see the code. So here's the PyTorch implementation. So the mean teacher, so generally the ideas are quite simple to implement, like in PyTorch or TensorFlow. So like the mean teacher, you have alpha, which is the parameter of the moving average. You have a model, and then with these, we create like optimize function, which basically just updates the weights with the moving average. And then in the bottom, we explain how you implement this interpolation method. So they usually use the mean square error as the loss. We create a mean teacher from the student model. So we just we do a deep copy of the student model, and then we go through the supervised data loader and the unsupervised data loader at the same time. We apply our typical supervised loss, and then we create an interpolation between our 2 unsupervised batches. And then we create teacher predictions on the batches that we have. And then we also create student predictions on the interpolated batch. And then, yeah, we interpolate the outputs of the mean teacher. And then this is our target in the loss, basically. And yeah, it's usually quite simple, let's say, to add it to your typical framework. And yeah, I'll pass the mic to Tomas.
Thanks a lot, Yassir. So yeah, the last method we overview before showing some real examples. Like there are also graph-based approaches. Yeah, so why graphs are interesting in this case? Just imagine, the data that you get on different problems. Sometimes you have connections between your labeled data and your unlabeled data. For example, think about, I don't know, a customer request processing system. You have requests from the same customer, so there's a link between them. Or you might have whatever problem, you have some same metadata on different data points. On, for example, if you think you're classifying Wikipedia content, you have these links from one Wikipedia page to another one. So there is some relation between them. So having this connection doesn't mean that these data points have the same label, but that there's a tendency to share a label. And then there are several approaches which benefit from these assumptions, like there are a bit more classical graph-based label propagation methods. Then there are newer things like neural graph machines, and there's the approach we show in the next slide, which is called graph agreement models. Yeah, so graph agreement model is something pretty nice, and the idea is you train an agreement model, let's call it G, that it does 2 jobs. First, it predicts if a pair of data points match, which means if they have a same label. So it actually takes 2 data points at the same time, and it would say if they are sharing the same label. So you can train this model like that, and at the same time, you can use this model as a regularizer for your classifier, let's call it F, by penalizing different predictions if a pair is predicted by G to have the same label. So if you look at the picture in the bottom, so classifier F kind of add confident predictions to your label set, and then the agreement model kind of regularizes the F so it doesn't overfit. If we look a bit more, let's say in a bit bigger picture, you can go from left to right. You can see first they train the agreement model G using the labeled data. They call it L. Then you can create a classification model F in this case, which uses L and the unlabeled data. So it considers the link between labeled and unlabeled data points, and also the links between 2 unlabeled data points. And out of doing this job, you will extend the L, grow your label set by adding the most confident predictions. Now, what is very interesting is that the paper states that you don't even need the graph provided. You can either use similarity metrics to kind of simulate a graph, which would be a noisy graph, or actually you can even assume you have a fully connected graph that each data point is connected to all other data points. Yeah, so that's one of the nice papers that has been published recently on the graph-based approaches. We got inspired from this paper and also from some other labeled propagation approaches, and we implemented some real example. So we are going to show some results on a data set called NLU evaluation data. You can get this data from Hugging Face. It's a data set of short utterances from conversational domain used to kind of measure the accuracy of different systems. You have about 25K data points and 68 intents, so it's not a super easy problem. Also, you have quite a lot of intents. And you can see examples of text and label in the bottom of the page. For example, wake me up at 9 a.m. on Friday. It would set an alarm as a label. You can say time to sleep. For me, like I thought initially this would also be an alarm thing, but actually you want to turn the lights off, and so on and so on. So we take this data set and we kind of simulate a few label problems. So first of all, of course, we split the data to 20% validation and 80% train set. But now the thing is we take our train set, keep 98%, kind of forget about their labels and assume they're unlabeled, and only keep 2% of the data as labeled data. So this is quite harsh. You end up with something like 400 something data points. This is about 6 data points per label, which is very little for kind of an NLP problem. Just to give you an idea, if you just fit fast text out of the box as kind of to get a baseline accuracy, you get about 50% accuracy. And in the experiments and results we show in the next slides, we mostly use BERT or BERT, which has been fine-tuned using MLM. So like we have a simple approach. Please don't read the text in the bottom, like it's for the recording, so we can go into details when we look at the video later. But the process works like this in the implementation we had. Is take the labeled data set, train your classifier out of this, also train an agreement model, which again, given 2 data points, it predicts if they have the same label or not. And then also construct a graph between labeled and unlabeled set. We use Elasticsearch for this, but let's not go into the details. And then you just say, out of this graph, which connects labeled and unlabeled data points, using G, which is telling you if 2 data points have match, run it on all of the pairs and give me the best pairs. And like you just take these best pairs and you add them to your label set and you repeat this process. So it's quite simple. What is interesting is that if you look at the results, so let's go first with fast text. So take fast text, it gives about 49 or 50% accuracy. You can use fast text as classifier, but just augment it with this agreement model. So you go in this iteration loop of adding labels. It goes to about 53%, which is like about 10% relative improvement or 4% absolute. Then you can, for example, take BERT. Note that BERT is already pre-trained on English content. So it already has a good classification accuracy of about 67% on this 2% of data. And if you now also attach this agreement model and loop over to add to your label set, you go to about 74%. You can also pre-train your BERT with MLM on the unlabeled data you have to improve the accuracy. So this you would get about 74% classification accuracy. But again, if you add this agreement model to your training setup, you go about to 76.5%. So in all cases, it would help to use this agreement model to add to your label set. Now, the important message here is that, like when you see where you see the red arrow, so what you see like is if you use 10% of the data as labeled data instead of 2%, which means 5 times more labeled data, and you use BERT, for example, which means you don't do extra techniques for using your unlabeled data, you get to about 75.7% of accuracy. While if you use still 2% of the data, which is 5 times less, but just combine your semi-supervised techniques, which in this case is MLM training and using this agreement model, you're better. So you're about 76.5%, which means you could get better results with less data. And this is quite a nice message for business use cases. Yep. So that's it for the results. The code, you can find it online on GitHub. So the conclusion. So labeled data is pretty expensive and it's hard to find. It has to be manually created sometime. So leverage your unlabeled data as much as you can. There are quite a lot of different approaches existing. It's a very active research topic. But also know that a lot of publications can overstate the power of these methods. So when you implement them, expect something like 10 to 30% relative improvement as a realistic target. You also need experimentation and a bit of implementing different tricks for each paper. So be ready to a bit do some small things for each of the approaches. And like considered all of these, we are trying to now implement and publish a library for few label machine learning, like DARTS, which is also from Unit8, but for time series forecasting. Yep. So that's it. Thanks a lot for listening. Now the floor is open for questions and answers. Billy, I think you're on mute. Back to you.
Yes, thanks, Moss, again. I said that, but I was on mute, so I said that again. Thanks, guys. I'm going to give you maybe 30 seconds, everyone. If you want to ask question, you can use the Q&A panel. We are really here for you, so feel free to write. Actually, I saw one question. Let me read that. Actually, out of all the approaches you presented, which one should be used when? Who wants to answer that?
Very nice. Yeah, it's a very nice question, and it's hard to answer. So I can give an opinionated answer. So you have some methods which are easy to implement and some which are more performant, let's say. So first of all, I would say there are things like this. If you, for example, work with NLP problems, like this MLM pre-training, I mean, they are almost off the shelf with like Hugging Face library, for example, you can implement rather quickly and they like rarely hurt. So that's a very good idea to use them. You can also try a bit the classic label propagation approaches. If your problem is not too complicated, they might help already. But at some point, these things will have a limit on how much they help. So then it comes to consistency and, for example, graph-based approaches. And here, like it's I don't have a clear answer. You have to try. Sometimes consistency helps. Sometimes it doesn't help much. The graph-based the same. Sometimes it helps. It does. Sometimes it doesn't. You can even combine them because they don't collide with each other. So it's really a matter of experimentation at that point with a bit more, let's say, advanced methods.
Thanks, Moss, for the answer. Guys, if you have more questions, we still have some time. You can write it on the panel. By the way, while you're thinking about some question, I hope that you enjoyed this session with us, that you learn a bit about machine learning with few labels, and that you also had some good time. On my side, actually, I can say that it was nice, and we really enjoy sharing our knowledge. Okay, more second. Second thing, so you will receive an email, and also the video gonna be uploaded on our YouTube channel. If you want to see all the other episodes, feel free to go on YouTube, Unit8. And actually today, it's our last webinar of the season 4 of Unit8 Talks. So that's a very emotional moment. But we're gonna be back at the beginning of the fall, probably with more content. So stay tuned. I see that there is no more question. So maybe Moss, you want to have a few words to conclude?
Yeah, I just wanted to say thanks to the speakers, Vincent, Yassir, and Billy. Thanks a lot, and also to the audience for listening and being interested in the topic. Feel free to reach us on LinkedIn or by email. You can see our contact details here on the page. Yep, thanks a lot and have a great day.
Thanks. Have a great evening. Have a great summer. We'll be back soon. Thank you, everyone.